I guess we can start.
No sound?
No, none, not at all. So, my name is Tomasz Borek, and I'm glad to be here, and I'm glad that you're here. It would be rather awkward to keep talking to an empty room. Thank you for coming. This talk is quite special for me because it actually stems from my problem, as in I kept listening to a number of conversations and they were like, functional programming is awesome. But they kept saying it in a very American way, like, it's awesome! And with that, it was like, I kind of shrank away from it because I'm a Polish person, and while sometimes we Polish people display affection, it's not to the level of American people who tend to like display it more. And I decided to actually come up with some honest answer to whether I need to bother with functional programming or not. This is version 4 of this talk, and I learn as I go, so every feedback is appreciated, and if you spot anything in this talk that is unclear or misleading or perhaps outright wrong, do not hesitate to tell me, please. I really will value your feedback, and I will use it, as I did with feedback from other installments of this talk. So who am I? On the internet, most often images associated with my name are those two. I'm sorry for this one. I really was not prepared. I'm also the leader of Lambda Launch Kraków, and I'm part of the Geekon team. Who here heard about Geekon? Yay, I like you. For the others, I will like you because you now also have heard about Geekon and most likely will come to Poland for it, because it's just very worthwhile. So, Geekon. I'm doing Geekon with other people from Polish JAG, which I happen to also run. And finally, I also participate in a group called Software Craftsmanship Kraków, which is an incredibly useful group when you want to broaden your horizons. Because Software Craftsmanship Kraków, at Software Craftsmanship Kraków, we do code retreats and we read papers. So I learned about memory barriers because one person who was much into hardware, he brought a paper and he said, this is insanely difficult, I cannot understand it. Let's read it and figure it out. So we spent like 2 hours figuring out how memory barriers really work. Or at other meeting, we actually spent 2 hours figuring how you can teach computer to teach itself like human brain. And yeah, just learning about human brain was quite enough. So, FP is awesome, as we all know, and if you ever happened to actually see quotes like the ones on the screen, then yay, I also did. So my favorite is, you're not a real programmer if you do not know FP. So yeah, it also reminds me about real programmers versus squish eaters, and how people who liked assembly language said that Fortran was absolutely totally useless and would never be accepted. Real programmers, as we all know, use butterflies, because you actually release your hand and the butterfly flaps its wings once, just once, then the tornado that forms on the other hemisphere actually makes the cosmic rays flip the precise bits that you wanted to be flipped. And thus zeros become 1 and 1s become zeros. So if you do not happen to use butterflies, that's okay, just go with FP. Now, as probably some of you know, there is an iconic term, silver bullet. So a silver bullet is something that you took with you if you actually ever went to hunt for werewolves. Because werewolves were just like unkillable unless you had silver bullets. So in a number of blogs and articles and so on, popularized by Frederick Brooks with his mythical man-month, this term in IT means like, this is the way to go and solve your unkillable problems, because it's just silver bullet. In my opinion, FP is not a silver bullet, but we may agree to disagree. Why? So I'll try to actually walk you through it. We already covered about myself and about the talk. I will walk you through the 3 most well-known FP papers, which actually provide quite nice arguments behind why FP is worthwhile. I'll also explain somewhat wishy-washy term like better language, like what it means that the language is better than other language. And I'll try to kind of provide some data on the usual claims you hear when you hear that FP is better, awesome, or you really need to change your job, skip whatever you're doing, and start learning FP. So, 3 most important papers would be Why Functional Programming Matters, Out of the Tar Pit, which again is a reference to Mythical Man Month, and Can Programming be Liberated from von Neumann Style? Who here read at least one of them? Okay, so you're in a good room, because my next few slides will be about those papers. So why FP matters, John Hughes, and to be honest, when I first submitted this talk, it was Lambda Days, and John Hughes was on the accepting committee. When I learned it, I was like, oh my god, I think I need to withdraw my talk. And fortunately, I learned that he said, oh, this will be interesting, I wrote a paper similar to this one. So yeah. What actually Hughes postulates? So first he says that FP matters because it's about applying functions. So you do not have side effects because function just returns value. You do not actually do something in the function that will change the world that you're coding in. So one function returns, no side effects. Now in FP you do not have assignments, says Hughes. So hence you have immutability, because once you actually have a value, it is like 5, and it will never be 7 or 6 or whatever else. It will also never be Tomek, because it's already 5. So once you actually assign the value, you cannot change it, hence immutability. Immutability again means no side effects. Now, he says that these are the usual things people say about functional languages when they claim they are really good and better than imperative languages or any other languages. Which is quite cool, but he says it's not enough. And I kind of agree, because in Hughes' opinion, the real benefit is modularity. Because when you're building programs, you need your building blocks, and you need a really good glue for actually sticking them together. So when you have those building blocks, you want them to be to flow. And that is achieved in functional languages with 2 mechanisms. One is lazy evaluation, and the other is function composition or pipelining. Whoever here used Unix, Linux, or any other distribution system, any other operating system like that? Okay? Now, who knows these concepts which can be very nicely outlined like that? Yeah? Number of hands. So, in Unix, you also had pipelining. You could actually stream the output of the command as an input to the next command. So you could go like that, or and input say, heck, your favorite script. Yeah. And with that, the something which is actually the result of the echo command will be pipelined to your favorite script, which will do whatever the magic you want it to do. And this is actually achieved in functional programming with function composition. So functions, being first-class citizens, may be used as arguments to the functions, may be used without anything that will contain them, be it object or anything else. And with that, you're pretty free in grouping your functions together and using them in pretty much any way you desire. So this is function composition. There is also another way, like for example, you can have function from a function, which is also cool from mathematical perspective. And usually at this moment, when there is a mathematician in the room, I see him nodding vigorously. But yeah. So lazy evaluation is the other glue that functional languages give us. And lazy evaluation means that you're actually postponing the evaluation of a value until you need to find out what the value is. So with that, you can actually do some pretty freaky stuff, like for example, operating on an infinite list. Because you never evaluate the whole list, so it can very well be infinite. You will be evaluating only till the moment you need it. Now, can programming be liberated? took another angle at the functional languages, but still, it actually ended up with very similar conclusions. So, first, do you guys happen to know von Neumann bottleneck? I see no hands in the air, so a short explanation. Most hardware architectures at the moment, they actually, I think I might even have it somewhere. Where would it be? Yeah, this will be kind of retro style presenting. Yeah, so von Neumann architecture is something that vast majority of CPUs currently are based on. There are variants of it, like for example hardware architecture, and it's still not something different, it's a version, it's a variant of it. The fundamental flaw, which is called von Neumann bottleneck, is actually this, okay? Because usually you feed inputs to the CPU does computation, and it returns the output. However, to do the computation, CPU very often needs to go to main memory, like RAM. When it does, it needs to travel through the bottleneck, which is the pipe, the bus between the CPU and the memory. Why it's a bottleneck? How do you think? Because it's too slow. Cool, it's actually a pretty cool answer, because over here, things happen in like nanoseconds. 1 nanosecond to actually do one cycle of a CPU, including the data access for a level 1 cache. 3 nanoseconds when we are actually operating on a level 2 cache. Amazing and very slow 9 nanoseconds to actually go to like cache of the 3rd level, which is still on the CPU. Now, when you go and when you actually try to access the memory, you're operating in like 100 of nanoseconds, okay? On the newest RAM sticks, it's like 78 nanoseconds to get there. And what is even worse is usually, while this is portrayed like this, it's actually 2 buses, the address bus and the data bus, okay? So first the CPU is actually asking for a memory address, it gets the address, and then it asks for the data at this address. So it's actually 2 trips, mostly, because CPU very often does not know the exact location of the variable that it needs. So with that, we have like a lot of empty cycles to burn on the CPU before we actually proceed with any real work, because we had to actually wait for main memory to respond twice. So with that, von Neumann bottleneck is an actual problem. And next observation that Bacchus, which is the author of Can Programming be Liberated from von Neumann style, next observation that he made was that you may have new languages, but those new languages, while they grow in size, like heavily, they do not grow in expressive power or new possibilities that they give you. So you may have like new control flow statements, you may have one more loop to do your looping, and that's like okay, but it doesn't really help you much. It isn't really an improvement over the previous loop, it's like a partial improvement. Like in this very specific case, you may want to do while instead of a while loop, because you will get the first walk through the loop for free. Wow. So he wasn't really impressed with it. Then he went on to actually observing that languages actually have some sort of framework and the changeable parts. And the changeable parts is very often what we programmers use to build software. Unfortunately, they lack something which allows us to combine forms. So when we speak in statements, we speak sort of like we do in imperative languages. Step by step. We give computer very precise sets of instructions to do our work, which is manipulating the variables usually. And now, Bacchus said that actually we want to go in something that allows us to combine the forms more, well, better. and he proposed functional programming languages. So that was the other paper. Now, final paper is out of the topic, and this paper actually offers a prognosis as what will be the future best language of them all. And they say that there are few ideas that we first need to realize. First is complexity. There is accidental complexity and essential complexity. Anyone wants me to skip it? No? Okay. One hand, but at the same time, two people were like, no, don't skip it. Sorry. So, briefly, whenever we tackle problem as a software developer, we have complexity that is given and essential to this problem. Like, for example, web server will have to actually talk on the web. And there is just no way around it. We will not code web server without tackling that. So this is essential complexity of it. However, if our web server will use like the newest, fanciest language in the world, and thus we will need to actually convert it into Java because our office actually has a policy that most codes should be in Java, so also our newer, fanciest language needs to talk to Java, then this is the accidental complexity. It doesn't have anything to do with the web server. It has something to do with our choice of tools. So accidental complexity is still complexity, and we need to maintain it. Complexity causes us to make mistakes because we need to remember about it, we need to understand it. On the other hand, in a number of cases, we cannot actually outrule accidental complexity because we live in an imperfect world. So people from out of the topic said that we're actually trying very often to lessen the complexity, to keep the software as simple as possible, to keep only the relevant parts. Yeah? And it helps if we do not have state. They say that if you have state, very often your accidental complexity will rise. While if you do not have it, you may forget about changing it, manipulating it, and thus focus on the real problem at hand, be it a web server or a calculator or a software that actually deals health insurance or whatever else. Now, state mutation and state sharing are the sources of complexity. Hence, if we can actually disable them, we're good to go. Hence, they like functional languages, but also they like declarative languages, like, for example, SQL or Prolog, because in both of them, you don't get any surprises. You declare what you want to happen, and that's about it. Yeah? Select from, it's like pretty clear what you're doing. So, what makes a language a better language? Languages are actually designed with some problem in mind. So we can actually divide languages into those of general purpose language, or a specific language, like language which is helpful in specific domain, or a language which is very good for statistical operations like R, MATLAB. And with that, I never really liked the expression that language A is better than B, because, well, if we compare, let's compare apples to apples and not apples to oranges. So whenever somebody tells you that functional languages are better, ask for what, or because of which operations you find them better, so that that person will actually explain his line of thought to you, rather than just offering a statement. Now, the usual claims about functional programming being absolutely a must is that it's the future or the next big thing. It is something that changes your thinking. It is another tool you will have at your disposal. It brings you to write shorter or terser code. It allows you to have more power and better abstractions, and it's more convenient this way. It has no complexity because you're avoiding state mutation, and with streams you get no side effects, and it's reliable because you can prove it, like mathematically prove it, and you can't beat mathematics. And finally, with multi-core and concurrency, FP is the way to go. Did I sum it up nicely, or anybody wants to add a claim? People normally don't. Yeah, okay. So let's define future. We can actually say that it's the future because of fame, like every conference has a Docker. Docker must be the future. Yeah? There are articles, like whenever you take a look, there are articles about, say, Docker, because I already used it as an example. You may actually take a look at the practical aspect of the future, like market share, domains of the market that this technology is actually found its appliance. You may take a look at who and where uses this particular technology to actually determine whether it has future, is the future or not. And you can take a look at job offers, which is again a pretty good indicator. Finally, you can take a look at language popularity, like take a look at the language which has a given feature and take a look at how many languages with given feature are popular, and at adoption level. So, the future by fame. Just those conferences here are pretty much functional in nature, with one possible exception of Strange Loop, which is a Strange Loop. Do you guys know Strange Loop? Some of you do, some of you don't. It's a very interesting conference. If you want to submit there, you better be a language creator or someone of similar level of skill. Yeah, so there are those kind of talks, and it's usually a conference when you go there, you exit it with like a warped mind. It's not mind which is blown, it's warped. It's twisted. It's like you're looking at things sideways. And it's actually quite incredible. So, judging by conferences, how many functional conferences appeared, how many conferences have a functional track, a Scala track, a closure track, things like that, you can see that, yeah, the fame is there from functional programming. Judging by the fact that articles about FP appeared even in mainstream portals, that, say, Oracle magazine prints out information about functional programming and shows how lambdas are it, yeah, again. By practicality, so market share. To be honest, I found no good and reliable data on market share usage. What I found I have later in the talk, who and where uses. I actually tried to get a feel out of a couple of lists which were dedicated to number of domains. So I know for a fact that whenever we have big data, usually functional programming appears in some shape or form. That is true for banking industry, that is true for larger companies which like deal with multi-million user bases, and that is also true for travel industry, so I can vouch for those. As for others, not so much. At least I have no data that would indicate so. Was it a question? No? Okay. So quality and quantity, like who would be using, I tried actually few things. Taking a look at GitHub repositories, taking a look at job offers at TIOBE index of language popularity. We'll actually come to it somewhat later. Adoption level. So Java, the lambdas that actually made their way into Java 8 were supposed to be released in Java 7. The fact that lambdas are really very popular, the fact that there was a library which actually allowed for lambdas to be used with Java 7 in like 2 months since the moment of their release, the fact that actually pretty much any major language has lambdas or closures in any shape or form. That actually indicates that programming with streaming is quite a convenient feature. Programming with streaming as in function, stream, function, stream, function, stream of transformation which leads you from your input to your output, to your final result. Now, SQL, which is an interesting feature, SQL had it like long ago in like 60s or something. Language popularity. This here is the clear indicator that Scala is the winner, right? I mean, look at it. The only language which actually crawled out of whole crowd is Scala. Oh, thank you for spotting that, Nicholas. Yes, my scale is absolutely very interesting because my scale is like 0.04. Now, let's take a look at this in context. Now here we have like 4 or 3 or 2 or 1, and this language, unfortunately, is not Scala. This language is SQL. This language is Java. Oh, sorry. This language is actually Java. SQL is this color, so orange. Yeah. So if we take a look at it's actually domain specific, and here SQL is actually an aggregate of like 3 different dialects. So a very good observation, by the way. What this actually shows us is that in context, functional languages like don't seem to amount to much when compared to other mainstream languages. This data, of course, ends at January 14th. But if we took some other languages in comparison, we would see that still not much. Even Ruby, which at the time was immensely popular, wasn't really faring very well in comparison to languages which have enormous code bases. So C, C++, Java, languages which are old, have like several years, 2 decades or more, there is really a huge amount of code written in those languages. And with old code bases, you don't really often rewrite it to something new, because to rewrite it is incredibly hard. And many companies decide to actually keep it until some new software can be obtained, which can obsolete parts of the other software. The other idea for popularity would be to actually take a look at GitHub repositories. Yeah, GitHub is immensely popular. Pretty much everybody nowadays has a repository on GitHub. So over here, I have a short statistic about active repositories and their languages. So as you can see, the ruler is JavaScript, then we have Java, Python, CSS, PHP, Ruby, C++, C, Shell, C#, Objective-C, blah, 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 Scala. Like, not in top 20. So with that in mind, we may be tempted to say, well, it's not really popular, any functional language is not popular. I would kind of agree to disagree because of the way GitHub actually assigns a language to your project. Have a short experiment. Create like 100 lines of HTML. Let's say that you're writing a single web page, and not a single web page application with Bootstrap and 4 other libraries. It's just really a simple HTML. Now add one JS library, say the most popular jQuery. And all of a sudden, you have like 100 lines of your HTML code and the jQuery library, which has more lines than 100. It's like few kilobytes in the minified version. And what GitHub then says is, oh, I recognize your repository as a JavaScript repository. Which kind of explains why the JavaScript here has such a large presence. GitHub info is a very nice page which actually helps you play with it, and here are somewhat updated data. So you can see that we have like more than 3 million of active repositories, more than 300,000 active repositories, more than 3 million of total pushes, and so on and so on. And interesting thing is that still the first language is like Scala, but somewhat lower. The answer to that lies in this and this. We need to remember when we actually take a look at GitHub and try to reason from its data that GitHub was primarily for Ruby people. So if you were a Ruby person, you actually had all your code on GitHub at the very beginning because it was actually a Ruby thing. Then when Ruby's popularity declined because Ruby on Rails became too bloated and too unsecure and too widely used to be really successful, they were kind of killed off by their own success. And with that, Ruby declined and other people became to use GitHub. And if we took a look at somewhat newer data with 2015 included, this is actually This is based on data that was collected up till August 2015. So like a year later than the previous graph. And over here you can see that Ruby really declined in popularity. And Java actually went from like 7th to number 2. And that, I believe, reflects the fact that A, Java people became using GitHub. 2, number of projects migrated from like SourceForge or Google Code to GitHub. And thus, number of open source projects looks like Java and JavaScript would be still the most popular if we count by the number of lines in particular language. TOB or TIOB, depends how you actually read it. How you people in Sweden read it? TIOB? I love it, it's like in Polish. TIOB, okay, so TIOB. TIOB is actually, in my opinion, the best source of data for language trends because of how they actually trend things and for how long they trend things. They like have the data since 1980 something, so yeah, 1985, and they offer yearly index or annually, and they offer trends, and they offer really good comparison of a number of languages. Now, I looked at top 50 languages, and in 2014-2015 it looked like that. So C, Java, C++, Objective-C, C#, JavaScript, PHP, Python, VB, .NET, VB. Okay. Now, taken from like 20 minutes ago, it looks like that. So we have Java, we have C, we have C++, C#, Python, PHP, VB, .NET, JavaScript, Perl, Ruby, and so on. Yeah. Now, in 2015, when I last gave this presentation, the most often, the highest on this list was F#, which was a Microsoft and still is the Microsoft language for functional and statistics, and was used in a number of big data operations. Now, F# was number 14th. Now it was actually outdone by R, which is number 16. But still, they have like 1.something% of total market, which is fairly low. So judging by market, okay, judging by market, it's not really good. How TOB actually calculates the ratings is that they use, they have like list of search engines, and they go to search engines and they check how many times in those search engines a query JavaScript programming was inputted, or insert a language programming. With that, they like they count the hits, they normalize them so that upper lower case will not matter, programming and learning programming also will be the same, and so on. And then they actually make sure that all languages add up to 100%. So that is how you can actually see whether people want to learn the language. So TOB is actually a fairly good indicator. Now, this already covered. So summarizing the theme. Yes, FP is clearly on the rise. It began like a few years ago. It actually can be reflected if you look into the data. However, it's nowhere near a must-have skill, and still the mainstream languages are pretty much untouched. Now the revolution, of course, comes from the fact that every now and then the new big thing comes, and take a look at object-oriented programming. Like, it was the next big thing, like when Java came up, and pretty much everybody were saying that similar things as people are saying about FP, they were saying about object OOP. And taking a look right now whether you need OOP to be a real programmer, no, you don't. There are cases when you actually use it, but there are cases when you do not. Fault bending and another tool. That was another claim that if you learn functional programming, you will become a better programmer. That is actually a very generic truth. You may apply it to swordsmanship, you may apply it to shipbuilding, you may apply it to programming. So yeah, I see no reason to actually disprove it. Of course, there are a number of personal statements like I learned Haskell and now I suffer, because in my company I program in like C#, and when I actually use functional composition and the next programmer comes in and he was like, okay, after 2 hours I understood what you did here, but why didn't you use a for loop? Because it would like achieve the same result. And it's like, oh, yeah, so I learned Haskell and I suffer, yeah. There was on MIT an interesting curriculum because they started with Scheme being the first language. Now they actually offer Python or I think Java, but I'm not sure. Still, with functional language being the first one, when you actually start programming, it makes you think differently. I've met few people in Poland also who actually were exposed first to functional languages, and they really were kind of stupefied. Like, for example, they took type inference, strong type inference, for granted, and they were like, how can you not know what type is this value? How? Like, what's happened to the compiler? Shorter and terser code. Pretty much every functional book and tutorial says that if you use my library, take a look, here is the long code that deals with this XML file, but with my library you're doing it in like 3 lines of code. And this is at some point very attractive, and I can see that. However, have you ever seen a program written in APL? So a program in APL would use number of symbols, and for example, inverted triangle, which was I think the large delta in Greek language. Patroklos can correct me if I'm wrong. And this inverted triangle would mean a matrix operator, like multiply a matrix by a matrix, or it would mean a string concatenation, depending on what is on the left and on the right. So it was really, really short and terse code, like 2 lines of code, and you had like thousands of operations, which was fairly cool, and you needed a special keyboard to actually write programs like that, and it really didn't fare very well. So shorter, using terse brevity of the code as an argument for offering this or other languages pretty much boils to where you are on a terse versus verbose axis. If you are close to the verbose languages because you like your language to spell out things for you and do not offer you any surprises, then you will clearly like languages which are close to natural language. And you will dislike mathematical formulations. On the other hand, they are cool for people who have strong mathematical background, because they look at Java code and they're like, wow, wow, what a heavy load of words. More power. Mm-hmm.
Everyone has the same understanding, it's good, but the thing is, most of the case, no.
It's not.
Not everyone has the same understanding, so we need
explicit versus implicit also offer one more thing, surprises in the code. If you have everything spelled out, you do not need to understand and know how it works underneath. You don't need to open the bonnet and take a look, oh, the engine is on this side. So if you may not do it, that's actually quite cool in some cases. But yeah, more power. Paul Graham, who was one of the guys who actually popularized Lisp, offered the blood paradox for it, which is kind of like that. We know that programming languages vary in power, because we have like version 1 and then version 2, which is stronger. So clearly that's that. Now, if we have a hypothetical language blob, which is right in the middle of the power axis, and if we are blob programmers, then we like blob for some of its features, and we look down on the power axis at the languages there, and we're like, ah, not bad, but it doesn't feature X of blob, like pattern matching, or it doesn't have lambdas, and blob has them. Now we look up to the stronger, more powerful languages, and we see like, these are weird, and usually that's how people actually perceive languages which offer more. There might be features which we like, but we never use them. They're out of our comfort zone, and thus, like, what's that? And Graham usually concludes it with, and at the very top of the axis, there is language with lots of parentheses. And if you happen to see Lisp syntax, which is his favorite, you know what he means by that. So, complexity means less bugs, and this is kind of it's kind of offered in a number of papers as a statement with some data which backs it up, but there have, at least I found, no really extensive study, similar to, for example, study behind generational hypothesis in garbage collection. So referential transparency, no or little side effects, that's cool. Reasoning about programs. Yes, you can, and no, you won't. No, you won't, because it's just insanely hard. It's just to prove that quicksort really work. O'Hare spent like 20 years. So it really ain't anything easy, and proving that your business software is actually working as client specified will be really, really hard. Unless you really went from the very get-go with mathematical language. Then you probably have nice formalism in it, and you can actually try to use, say, Yoneda lemma to prove that this construction is equivalent to that construction, and based on that mathematical theory, I can actually argue that. But I see no business adopting that as their main feature. It solves multi-core problem because it's immutable. It has less state, less deadlocks. And yes, again, papers verify that with data to some extent, but no extensive studies had been made. I've actually contacted Erlang people because Erlang is like a language which was adopted for telecommunication. It's a functional language, and they most likely have the data, but so far I got nothing. Unusual claims is that hybrid approaches are the next best thing, like for example marrying functional programming with logic programming, and that will actually allow us to have programs which are nicely glued together, and we may actually reason about what's next. Also, there is a number of papers which actually show that good OOP as you intended, as the author of the term object-oriented actually meant it, would be very, very similar to good functional programming, because you also would have like streams of messages between objects which would actually amount to the same thing as functions in functions. Summarizing. What is logical can be inferred, so you can actually talk about concurrency or complexity. You can back with data that proving it will work in some cases, but only some cases. You can argue the power or expressiveness because it's actually de gustibus, which means to each its own. And you can argue that it gives you another perspective. It's pretty much very easy to do so. Terser code or market share or language being popular, not really good arguments. First 4 points are actually my point of view, because it would be kind of silly not to tell you what I feel about this, since I talked so much. And the real answer actually depends on your case, so you tell me or pretty much any other person. With that, thank you very much.